Okay, yes, today we will do 3.6, which is on the easy side, and 4.1, which is on the medium side. It's not too easy, not too hard. Now, variations, we will be dealing with three types of variations. The first one, direct variations. Or sometimes we also call proportional. That's the one of the keyword. Is as the following. We say, for example, the phrase will be X and Y are proportional, or we may also say X varies directly as Y. Now, when we see this phrase, it means X is a constant multiple of Y, where the constant multiple there, the K there, is called coefficient of variation or constant of variation. Let me see what the term the book use. Our textbook, different textbook use different terminology, but the same meaning. Oh, our textbook use constant of variation.
Por eso te digo que esa cosa de afuera hay que limpiar, porque tú nunca sabes. Ay, lo que yo le he hecho, cuando ando con el spray.
Okay, where this K should be positive. Should be positive. In this sense, it means the following. When we say they are proportional, means if X increases, then Y also increases. Okay, both of them increase at the same time, or both of them decrease at the same time. Okay, now let's say, for example, if I pick question number 2, what's my pointer by the way? Number 2 in our textbook, that's on page 241. It says that S varies directly as T. S varies directly as T. It means S equals to a positive constant multiple of T. Now then, when we read further, it says that T equals to 10 when S equals to 18. Now it means 18 equals to K times 10, therefore the K is 18 over 10. Let's use decimal, 1.8 equals to K. Now once we get the K, then we update the equation. Then S equals to 1.8 T. Now this is the equation of the variation, while the K stands for the constant of variation or constant of proportionality. Now you see that if I increase the T, for example, if I change the T just for fun, suppose I change the T by, I double it. Let's say the T, I change the T becomes 20, which is double of that. Then what do we expect the S to be? What we can see, for example, if I plug in the numbers, S equals to 1.8 times 20. That will be 36. Right? Now you see what I said earlier, if we increase the t, then the s will also be increased. In fact, if we doubled one of the variable, then the other variable will get doubled too. Okay? Now if we triple one of the variable, then the other variable will get triple. Now that's for direct variation or proportional. The second case, inverse variation. Or we also another phrase that we use, inversely proportional. Inversely proportional. Now the phrase usually has the following: x varies inversely as y, or another phrase, x is inversely proportional to that means x equals to k over y. Again, where the k is the same for the k that we have above, we call that constant of deviation, and the k has to be positive. Okay, now when two variables are inversely proportional, like x and y are inversely proportional, it means when x increases, the y will decrease. Vice versa, when x decreases, the y will increase. So that's what we mean to say these two variables are inversely proportional. Some little note that our textbook does not mention, good to know, maybe useful, is that if x and y are inversely proportional, so I take it from here, it also means the product is constant. While if they are directly proportional, it means the quotient is constant. We can say that x over y equals to constant. Okay, that's why to keep if they are directly proportional, then if one of them increase, the other variable has to increase to keep the proportion. While when they are inversely proportional, if one of them increase, the other variable has to compensate that such that the product is still the same k. Okay, now let's see, for example, from our textbook. Let's see question number why I don't really see. I want a simple question. I can't really find one. Then let me make my own example then. Let's say B and T are inversely proportional. v equals to 60, the t is 3. And the first question is find k, the constant of variation. Second, find the equation. And then the third one, find t and v equals to 80. Let's say if we go up, and first part, the v equals to 60, t equals to 3, because they are inversely proportional, means v equals to k over t. 60 equals to k over 3. So the constant of variation will be 60 times 3, which is 180. Now then, what about the equation? Just plug that in, then v equals to 180 over t. That's the equation. And then the third, when v equals to 80, what is the t? So 80t equals 180. So t equals to 180 over 8. What's that? 90 over 4. 22.5. I'm sorry, 2. What am I doing? Am I missing something? Oh, I'm missing a 0 here. So I will get 2.25. Now I use v and t here for velocity and time, for example. Suppose I want to drive to somewhere, and we know that if my average speed is 60 miles per hour, it will take me 3 hours. Then what happens if I drive 80 miles per hour? How fast will I arrive? And I will, from what we have here, I will arrive in 2 hours and 15 minutes, 2.25 hours. Okay, now you can actually see these examples a lot in intermediate algebra, algebra 2, for direct variation and inverse variation. You see this a lot actually in algebra 2, direct variation and inverse variation. Now, for us, however, we will work more on the joint variation. Now, joint variation, basically the combination of those two. I think I will do 2 examples from there, and we go on to the next section. So the third part is joint variation. Let's say, for example, I pick question number 6. It says that W varies directly to SZ, and inversely as the square root of U. This means what? It means W is equal to K times C, because it varies directly as C, and inversely as square root of U. Inversely as square root of U. That's what it means. Now, how to solve that further? We did the same idea like earlier. Let's say, for example, here it says that when C equals to 2, U equals to 9, W equals to 6, and 6 equals to K times 2 over square root of 9. Okay, so when I solve this, I think K equals to what? K equals to 9. Okay, and therefore we can update our equation to be W equals to 9Z over square root of U. Okay, now that's the equation of the variation. This is the constant of variation. Now let's do one more question or two more questions. I see a good question earlier, number 13. Number 13, it says that Q varies inversely to the sum of x and y, so x plus y. Now if you read this sentence, then we get Q equals to K over the sum. Okay, and then from there we go on. Would you like to pick any questions from this section, maybe? Some word problem? Okay, nobody say anything there. Oops. Oh. Number 16, okay. Number 16. Y is directly proportional to the square of x and inversely proportional to the square root of z. Because it is directly proportional to the square of x, then y equals to kx squared, inversely to z. So that's over square root of z, then that's the equation. By the way, this is my notation for proportional, and my notation for inversely proportional. This is mine though. Not every teacher actually follow this. My notation for inversely proportional is this. Okay, so it's this one here is actually commonly acceptable for directly proportional, but this one, inversely proportional notation, the one I use, is not really. Some teachers actually use the following for inversely proportional. For inversely proportional, they tend to use the following. Y inversely proportional to square root of c, they say it's proportional to 1 over square root of c. Now, that's how they say y is inversely proportional to square root of c. In the exam, would I like you to do that? It's up to you. It's up to you. I even think that from the question, I was just so lazy to write the question down, right? So I summarize my notation. Instead of writing in words, I write it in this summarized notation. But what you really need to give me is actually this one. Okay, and then from this number 16, there's a follow-up when x equals to 5, z equals to 16, then y equals to 10. then you did what we did above to find the k. I think that one you can do yourself. Okay. Now let me go on to the next section. Is it recorded by the way? I believe I recorded. Yeah. Okay, let's go on to 4.1 inverse functions. In this inverse function, I will discuss a couple of things. This section is supposed to be a short section, but once you put it in my hand, it becomes a quite long section. What are the things we'll cover here? First, I will cover what we call a one-to-one function. And of course, from there, we will talk about the definitions, what is one-to-one function, and the horizontal line test. One-to-one theorem. And of course, some examples. Now, after that, then we will talk about inverse function. First, of course, the definition and some simple example for notation. I think I need to do notation after definition, notation, simple example, how to find inverse function. From here, the one that our textbook does not really talk about is some improvisation. Maybe instead of improvisation, let me call that variations of topic. Oh, using this inverse function, we will also talk about the graph. So before we get into the variation of this topic, we will talk about the graph. Okay, now what is one-to-one function? A function is one-to-one. A function is one-to-one if each element in the range corresponds to exactly one element in the domain. Okay, now let's review a little bit about the definition of function. Now, a function is the relation from one set to another set in which each element in the domain corresponds to exactly one element in the range. So let's say we have, this is the range here, and this is the domain. Then each element in the domain corresponds to exactly one element in the range. Now, this is a function, right? Because every element in the domain, every element here corresponds exactly to one element in the range. But even though this is a function, this function is not one-to-one. This is not one-to-one. Now, the reason is we can find some element in the range. This element here, for example, corresponds to two elements in the domain. See, it is a function, but not one-to-one. Now, how to make it one-to-one? Then a function is one-to-one if, oops, sorry, a function is, let me erase that, I don't like that. A function is one-to-one if from the domain, each element in the domain corresponds to an element in the range, vice versa. Each element in the domain corresponds to one element in the range, and each element in the domain in the range corresponds to one element in the range. Let's say something like this. This is a function, and it is one-to-one. Okay. Now, here's the thing, though. Some common misunderstanding. The way our textbook explain it, and I believe the way other instructors explain it, and there's a tendency in our understanding that when we talk about one-to-one function, one-to-one, it has to be a subtopic of a function. It is true for the purpose of our discussion. So from the point of view of a function, then let's talk about one-to-one function. But it is actually two separate issues. You can find a one-to-one relationship, which is not a function. Let me say it again. We can find a one-to-one relation, which is not a function. Now, the following is one-to-one relation, which is not a function. So let's say I have this guy here, okay, and this guy here, in which from the domain it goes to two elements in the range. Now this is not one-to-one. I mean, this is not a function, but it is still one-to-one. This is still one-to-one. Of course, we will not talk about this type of relationship. This is one-to-one, but not a function. Okay, so that's what one-to-one about. One-to-one, and of course the topic that we talk about here is a one-to-one function. Now, if a function is one-to-one, then how do we see that graphically? A function is one-to-one. A function is one-to-one if its graph satisfies horizontal line test. Now, what is horizontal line test? Horizontal line test is each horizontal line intersect the graph. Each horizontal line intersects the graph at most once. Okay, let's see some example. For example, y equals to x squared. We know the graph looks like a parabola. It is a parabola. Now, if you want to know if this y equals to x squared, which is a function because it satisfies vertical line test. Now, but is it a one-to-one function? What we can do, we draw a horizontal line. Now you see that this horizontal line, we can find a horizontal line that intersects the graph twice in this case. Therefore, this y equals to x squared is not one-to-one. Now, how about y equals to square root of x? The graph of y equals to square root of x look approximately like this. Now, is that one-to-one? It is a function because it satisfies vertical line test. Every vertical line intersects the graph at most once. But how about horizontal line test? If we draw a horizontal line test, horizontal line, notice that it intersects at most at one point. Now, I use the word at most at one point because it is possible you can find a horizontal line that intersects nowhere, right? Okay, now, but we talk about if it intersects, it will intersect at only one point. Then it is a one-to-one function. Now, in our earlier discussion, I mentioned about a relation which is not a function but one-to-one. Y squared equals to x. Y squared equals to x. Now the graph is I don't know. The graph is as the following approximately. Here's the curve. Now I have to do the graph of x squared, y squared equals to x, approximately like this. Now notice that this is not a function because it does not satisfy a vertical line test, right? It's not a function, yet it is a one-to-one relation. One-to-one relation because every horizontal line, every horizontal line that I graph, it hits the graph at most at one place, right? Okay, so this is a relation, not a function. Not a function. But one-to-one. Okay, now, the emphasis of why I give you this example, the reason I give you this example is to show you that function and one-to-oneness are actually two separate topics. Now, but if you have a special case where you have a function and one-to-oneness, then later on we can talk about inverse function. Okay? There's a theorem that I almost missed earlier. Let me write it here. One-to-one theorem. If a function fx is continuous and increasing, or decreasing, on an interval, then let me call it on interval I. Okay? Then the function is one-to-one on that interval I. Okay, so let's say, for example, we have this graph, the graph of a linear function. Actually, a linear function is a one-to-one function. It's a one-to-one function, and it's continuous everywhere, which means every horizontal line will intersect the graph at most at one point, right? And therefore it is a one-to-one. Yeah. Now that's for linear function whose slope is not zero. What happens if we have this kind of function? Something looks like x squared. Okay, x squared actually looks like this, right? The graph of x squared. Okay, but if I restrict the domain, from 0 to infinity only, then you see that in this interval, it is a function, and it is strictly increasing. Right now, if it is increasing, then it is one-to-one on that interval. Now, in fact, if we look the other way, if I restrict the domain of this y equals to x squared to the other side of the interval, from negative infinity to 0, you see the graph is actually decreasing there, right? If the graph is decreasing there and continues, then this function is one-to-one on this interval. Okay, on this interval. Now, then how do we go from this one-to-one function to inverse function? Here's the thing. Function has maybe I say from start. The inverse of a function always exists, but may not be a function. the inverse of a function is also a function only if the function is one-to-one. Okay, now before we talk about inverse of a function, one-to-oneness, and what inverse function, let's talk about what is inverse function first. Definition: a function gx is the inverse function of fx if gx undoes what fx does. As if we are saying the following. Suppose this is the domain for fx and this is the range of fx. Domain and range of fx. So let's say half from the domain goes to the range by fx. Now gx will send that back. Okay, that's what we mean by inverse function. Now, and if g is the inverse of fx, the notation will be gx is the same to f inverse of fx. Okay. With a note, in fact, that's a big note, that f inverse x is not the same to f inverse x is not the same to 1 over fx. Now, 1 over fx, if you want to use the -1 exponent, should be written as fx to the power of -1. Okay, but inverse function of fx is not 1 over fx. Okay. Now, let's say, for example, how do we use this this idea here? Suppose, for example, let fx, it has to be a one-to-one function, be a one-to-one function. It implies we have inverse function, right? There is gx inverse function of that function fx. Suppose that f3 equals to 5. It means g5 equals to 3. If the function sends 3 to 5 in the range, 3 goes to 5, then the inverse function will send 5 back to 3. We can also write that G5 equals to 3. We can also write that as F inverse 5 equals to 3. Okay? Now, uh, how do we find inverse function? I think I want to talk about that first. How to find, if we are given a one-to-one function fx, how do I find inverse function of that function? Okay, I will need you to find, when I ask you to find inverse function of a function, then I need you to write it in 4 steps. In fact, I want you to write it 1, 2, 3, 4. Okay, the first step is rewrite fx by y. Let's say for example, I have this function here. Let's say I have, for example, find the inverse function of fx equals to 2x minus 1. Then the first step is replace that fx by y equals to 2x minus 1. The second step, swap x and y. So x becomes y becomes x. Okay, please write this down, especially the one here, Please write this down because I will come back here later on. Now, the third step is solve for y. So in this example, x plus 1 equals to 2y divided by 2, 1 half x plus 1 half equals to y. Or you can also say y equals to x plus 1 over 2. Okay, and then step 4, the last step, rewrite y by f inverse x. That's our step 4. F inverse x equals to x plus 1 over 2. Okay, now that's the procedure to, uh, find inverse function of a one-to-one function. Now, let's do some problem first from here, and then I explain more. Let's say, for example, I pick question number Number 32. Number 32. Number 32, find the inverse function of fx equals to 4x over x minus 2. Actually, if you think about this, we have done, especially for this question, we have done the similar procedure in the past. Find inverse function. The procedure is quite similar, of course, but that one is something we did not related to this inverse function. Now, so step 1, I replace the fx by y. In your test 1, I have a question similar to this, but at that time I asked you to solve for x. Now here, before we solve for x, actually solve for y, we swap the x and y first in step 2. And now we solve for y, which was originally our x, right? Yeah, so first step, I replace fx by y. Second, I swap x and y. X becomes y, y becomes x. And then in the third step, I solve for y. So x times y minus 2 equals to 4y. xy minus 2x equals to 4y. Xy minus 4y equals to 2x, and continue here, and y times x minus 4 equals to 2x, so y equals to 2x over x minus 4. Now, and then my final step, f inverse x, replacing y by f inverse x, equals to 2x over x minus 4. Okay, now that's for number 32. Let's do more. In fact, what we have done so far is basically what you learned in intermediate algebra. Now, what makes precalculus different from intermediate algebra? Let's take a look, for example, on number 38. 38. Find inverse function of fx equals to square root of x plus 4. And the x is restricted to be, of this function. Now, step 1, I replace the fx by y. Step 2, I swap the x and the y. Step 3, I square both sides. And then subtract by 4. I solve for y, right? And step 4, I get the inverse function x squared minus 4. But there's a problem here. There's a problem here. What problem? We know that the graph for square root of x squared minus 4 is a one-to-one function. It looks like this. And the quote-unquote vertex is negative 4, 0, right? The y-intercept is 0, 2. Now, the thing is, the inverse of a function has to be a one-to-one function also. The inverse of a function has to be a one-to-one function also. While when we see this function here, this is not one-to-one. So what kind of mistake we make? Actually, not on the mistake, but on the restriction. Notice that This function is 1 to 1. What do we know about the y? The y has to be at least 0. Is it right? I mean, that's the consequence of that function. The range is at least 0. Now, if the range is at least 0, when I replace x becomes y becomes x, then the y becomes x here. You see that? This guy becomes this. Okay? And that's what we need to carry over all the way. Now you see that once I restrict this function, x squared minus 4, then it is a one-to-one function. Okay, so this is the fx. Now f inverse x should be x squared minus 4, but only on the positive branch. Oops. Only on the positive branch. Without the restriction that we make that x has to be at least 0, we will end up with not a one-to-one function. You see what I mean? But no, we need to get rid of this. This part here, not right. It's not right. We have to get rid of this. Now, I don't want to use that color. Sorry. If I don't do that restriction, then we will end up with a full x squared function. Okay, but that's not one-to-one. Now, the inverse of this not one-to-one function should not be a function. You know, remember our discussion earlier. So in this case, you have to pay attention to the restriction. In this case, the range is restricted. Now, let's do another problem similar to this, very close to this. For example, if I ask you, find inverse function of, let's see, number 34. Find inverse function of 5x squared plus 2, where the x is greater equals to 0. Sorry, I didn't write it right. Let fx equals to this function, find inverse function. Now the question is, they already give us a function, why do they need to tell us this thing? Well, it has something to do with the fact that the function 5x squared plus 2 is not one-to-one. That function 5x squared plus 2 is not one-to-one. It is not one-to-one. So it is actually something looks like this. Okay. Now I don't graph that accurately. I just try to show you the situation. Now the reason they have to make this restriction here, the reason they need to make this restriction here is because if I don't make that restriction, then I deal with the whole parabola. But with that restriction, I will be dealing with only this branch, only for x greater equals to 0. Okay, so not this branch, not this branch, not this branch. Okay, not this one. Now, once it is a one-to-one function, then I can find the inverse function. But at the same time, we need to pay attention to that restriction though. Okay, step 1, I will replace the fx by y. Step 2, I swap x and y. Step 3, I solve for y. So y equals to square root of x minus 2 over 5. Now, when I apply square root property, then I'm supposed to put plus minus here. Is that right? But once I put the plus minus there, notice that, is it a function? I mean, if it were a function, then I have the right to use inverse function notation. But no, that's not a one-to-one function, because for some x's, actually for most of those x's, let's say x equals to 7, when x equals to 7, then the y will be 1 and negative 1, right? But no, it's not supposed to be, because if the function is one-to-one, the inverse function should be one-to-one also. Now, where's the problem? That's because we forgot to include the restriction that x has to be at least 0, which then changed to y at least 0. When we swap, the x becomes y becomes x. Do you see that? Okay. Now, but when y is at least 0, it means I will only take the positive branch, not the negative branch. Okay, because my y has to be at least 0. Right? Okay. Therefore, in my answer, I cannot include the negative branch, just the positive branch. Okay, just the positive branch. Maybe let me emphasize that here. I just use the positive branch, which of course we can omit from our notation. The square root without the plus sign in front of that means the positive branch. Okay, let me write that negative branch there. Okay, and then I put this notation here, and I say that need to cross out the negative part. Okay, why? Because we know that the domain originally from 0 to infinity only, at least 0. Okay, so when we do the inverse, then the range will be from 0 to infinity also. Okay, now I would like to us to take a little break. Let's take a break. We come back at, right now it's 10:37. We come back at 10:50. Now, when we come back, we will talk about some variations of this, but more things to say. For example, then using this inverse function, how do I find the range of the original function? What actually happens with the graph of inverse function, so on and so forth. Okay, see you later in approximately 10 to 13 minutes. Now, what we will discuss now in this later part is the following. Let me type what are the things we will discuss. First one, what happens to the graph of fx when we do inversing. So when we do inverse function, then what will happen to the graph? And of course, all the possible consequences from there. And then the next thing we will discuss after that, this is what makes our lesson different from intermediate algebra, is what if the function is not one-to-one. Of course, the inverse is not a function. Okay, but is there? But then, is there anything you can say from there? That's what we will see after. Now, let's see what happened when we to the graph of the function if we do inversing. Let me ask you to look back to one of our example earlier. One of our example earlier was fx equals to 2x minus 1. Now, can anybody remind me what is the inverse function?
It's x plus 1 over 2.
X plus 1 over 2.
X1 over.
Okay, now let's take a look what happened if I look at the graph. A second. So look at the graph, y equals to 2x minus 1. And okay, the graph of y equals to 2x minus 1 is this. This is the graph. What's the x-intercept? What's the x-intercept of this function? What is this here?
1/2.
To be more precise?
1/2 0.
1/2 comma 0. How about the y-intercept?
Negative, or 0 negative 1.
0 negative 1, that's right. Okay, now let's then take a look on the equation of the inverse function. That's y equals to x plus 1 divided by 2, which is actually, you can see that as 1/2 x plus 1/2, right? Now, and you see here, this is the graph of the inverse function together with the function. Notice that the original x-intercept, 1/2 comma 0, now becomes the y-intercept, 0 comma 1/2. And the y-intercept originally 0 comma negative 1 now becomes x-intercept negative 1 comma 0. Now, why does that happen? The reason is because when we look back into our procedure, the procedure of x becomes y, y becomes x happens in step 2. What's that? So when we swap x and y, when we swap our x and y, That's the infer. That's where the inversing actually happened. Okay. Now then, when we swap x becomes y, then what actually means is that our domain becomes range, range becomes domain, x-intercept becomes y-intercept, y-intercept becomes x-intercept. So anything related to y becomes everything related to x, everything related to x becomes everything related to y. Okay, so that's why when I teach how to find inverse function, I want you to write it in these 4 steps, not 3 steps, not 2 steps, not no steps, not just like like this. No, I need you to write step 1, step 2, step 3, step 4. Okay. Now in your test one, there were problems. I think 3 problems in which I asked you to solve non-linear inequalities. And a lot of you didn't do it the way I taught you. Like I need you to write step 1, critical numbers, step 2, sign graph, step 3, the solution. Now, a lot of you didn't do it that way. And yeah, I penalize a lot, okay? Now then, and not only I penalize a lot of you actually get wrong answers and you don't realize what's wrong with your answers. Now, I will not tell you what's wrong with it. You can look at my solutions. Okay, but I need you to write that step 1, step 2, step 3. Now, likewise, in this type of question here, when I ask you to find inverse function, do it in 4 steps. And I have a reason why I want you to do it in 4 steps. Now, one of them is when I try to teach you some concepts. Now, what happened in step 2? Now, in step 2, we swap x and y. And what happened to the graph? Well, then the domain becomes the range becomes the domain. Let's take a look again. The domain becomes range, range becomes domain, x-intercept becomes y-intercept, y-intercept becomes x-intercept. Now, in fact, if we want to say even more, what happened to the graph is we reflect that with respect to y equals to x line. We reflect the graph to y equals to x line. Make it a bit smaller. Okay. Copy graph. Give me a second. I want to bring this back to our graph here. Now, so you see that our x-intercept now becomes y-intercept. Our y-intercept becomes x-intercept. In fact, any point you choose here, let's say this guy here, if I choose a coordinate here, this is 2, 1.5. When I do the inversing, it becomes 1.5, 2. Now that's the effect of swapping x and y. The solution for my test 1 is I posted on our discussion last time, the one from March the 30th, on the discussion main page, main board. You will see that's a link to test 1. I think you can also find it on the file folder. Okay, do you find it, by the way? Whoever asked this question? Rick?
I'm gonna look right now, but
okay.
I'll find it. Thank you.
Okay. If not, then let me know. Yeah, because if you don't find it, then nobody found it.
Okay, thank you.
Then coming back here. So step 2 actually doing the reflection with respect to x equals to y line. Now you can think of that as a new transformation actually. Okay. Now let's go on. Let's take a look on another further example. one of the other example we did was, I believe, example 2, if I don't misrecall it. You know what, I don't want. As I remember, our example 2 was number 32 or 36 or 34. Number 38. Number 38, we saw that y fx equals to square root of x plus 4. And then we found out that the inverse function, therefore, was x squared minus 4, where the x is at least 0. Right? Now, we did that earlier, right? Okay, now let's take a look on the graph. Let's take a look on the graph. This is y equals to x squared. Is it minus 4? Yeah, minus 4. And then the other one is square root of x plus 4. X plus 4. Okay, now the graph I know is a bit too much. Let me screenshot this. Get the graph. On the graph. And then put it back to my. Now the thing is, because of the restriction, then we don't have this part here. Oops, I cannot erase that. So let me use this color. I will need to erase this. This is actually not part of our inverse function. This part here is not part of our inverse function. I don't like that color. Because we have two purple colors right now. Let me use another color. Let me use green color. Okay. So the one I covered in green is not part of the inverse function. Remember, do you know why it's not part of the inverse function? Because when we look back, the inverse function has that restriction that the x has to be greater than 0, right? Because of this, right? So we only take the positive branch, not the negative branch. Okay. Now let's analyze these graphs here. Notice that the x-intercept of the original function, square root of x plus 4, then becomes the y-intercept of the inverse function. Do you see that? Negative 4, 0 being reflected now becomes 0, negative 4. So if we know the x-intercept of the original function, then we know the y-intercept of the inverse function. The y-intercept of the original function is 0, 2, reflected with respect to that y equals to x line. Then the inverse function now becomes 2, 0. Okay, Now, to say even more, now let's take a look on the graph. What can we say about the domain of the original function? Anybody can help me? Which is the original function? The blue color, right? I'm sorry, not the blue color, the purple color. The purple color. This is the original function. What is the domain?
Negative 4 to infinity?
Negative 4 to infinity, including negative 4 or not?
Yes.
So it's from negative 4 to infinity. Now, how about the range of that function?
0 to infinity?
From 0 to infinity, that's true, including 0 to infinity. Now, take a look on the inverse function now. What is the domain and range? What is the domain of the inverse function?
Domain is 0 to infinity.
From 0 to infinity. And how about the range?
Negative 4 to infinity.
Now, I hope this actually emphasizes the concept I said earlier that when we do the swapping x and y, then the domain becomes the range becomes the domain. Now, take a look here that the domain of the function relates to the range of the inverse, while the range of the function relates to the domain of the inverse. They are the same for range of the function and domain of the inverse. And also the domain of the function is equals to the range of the inverse. You see that?
Yes.
Okay. Now, so this gives us another method. This gives us another method to answer the following question. Suppose, for example, I want to find the range of fx equals to, let's say, 2x minus 3 over 4x minus 5. Now, one way is to graph this very, very accurately to find the range. Another way is, what we can do is we find the domain of the inverse function, right? Now then, how do we find the domain of inverse function? Well, first of all, find the inverse function. Let me give you like 3 minutes to find the inverse function of this function. And then from there, we see what's the domain of that inverse function. Now, domain of that inverse function will be the range of this function. Okay, let me ask you to do that. I give you 3 minutes. So step 1, y equals to 2x minus 3 over 4x minus 5. Step 2, x equals to 2y minus 3 over 4y minus 5. Step 3, let me do it here. So 4xy minus 5x equals 2y minus 3. 4xy minus 2y equals to 5x minus 3. Factor the y. So y equals to 5x minus 3 over 4x minus 2. So the inverse function is 5x minus 3 over 4x minus 2. Now then, what is the domain of this inverse function?
Is it all real numbers except for 1/2?
It's kind of been back and forth. We're not really sure what the next couple of weeks are gonna bring us. Either, you know.
Hello? I heard a female student talking earlier. What's that about? Well, okay. Somebody say something. All real number except? All real number except 1/2. That's right. All real number except 1/2, because the denominator cannot be 1/2. Is it right? Now then, that implies the range for the function is also all real numbers except that 1/2. Okay. Now, but when we write that using using set builder notation, well, if we use interval notation, they will look the same. That will be negative infinity to 1/2 union 1/2 to infinity. Right? They are exactly the same. Now, but when we write that using set builder notation, we need to be a bit careful. When we use set builder notation, the domain is on the x where x cannot be 1/2, right? Okay, but when we write for the range, it's y where y cannot be 1/2. Okay, if we use set builder notation.
Now the question I have is, how will I really check who has actually done the check mark for the DLR?
I heard some of you talking about check mark. Let me see. What check mark, by the way? It should be fine. Okay, let me go on then. Let me go on. Then here's the next issue though. Oh, you know what? Just for fun, let's take a look on what the graph look like. Give me a second. I have a question. Oh, yeah, it's a background. Oh, I see. Background noise. Okay. Well, then don't worry about it then. Let's take a look on what they should look like when we actually graph them. When we actually graph them, let me erase this function first. Get rid of this function first. Well, you're supposed to be able to graph them already, right? That's actually part of our lesson last time. Okay, now, but if we do it here, what is the original function? I think it's 2x minus 3 divided by 4x minus 5. Is it right?
Yes.
And the graph will look like this. That's what the graph look like. The horizontal asymptote is 1/2. Y equals to 1/2. Right? That's the horizontal asymptote. While the vertical asymptote, x equals to 5/4. Okay. Now then, if then I graph the inverse function. What is the inverse function? Y equals to what? Is it
5x minus 3.
5x minus 3 over
4x minus 2.
4x minus 2. Oh, it's kind of like a complicated graph, huh? But that's why we need to look into this. Notice that. You know what? Let me copy this. Copy the graph and put it in our notes. Now notice that our original function x-intercepts here now becomes the inverse function y-intercept. Now, and our original function y-intercept now becomes our inverse function x-intercepts. Now, the domain of our inverse function, is x equals to all real numbers except x equals to 1/2. That's the domain of our inverse function, right? Which is the range of our original function, all real number except y equals to 1/2. Okay. Now, actually, let me emphasize one more. What does it mean that when we say that the domain, of fx is all real numbers except 1/2? I'm sorry, I think I said it wrong. The range, not domain. When we say the range of the function is all real numbers except 1/2. Now, what does it mean? It means when I set the function to be equals to 1/2, set the function to 1/2, we should get no solution. Yeah, when we say the range is all real number except 1/2, it means no x that give us y equals to 1/2. No x to give y equals to 1/2. Now you can try when we set the function, original function equals to 1/2, and we try to solve it. When we try to solve it, we will get no solution. 2x minus 3 times 2 equals to 1 times 4x minus 5. So 4x minus 6 equals to 4x minus 5. Cancel the 4x, I get -6 equals to -5, which is a contradiction, right? Therefore, no solution. Okay, now if we don't know how to find the inverse function, therefore we don't know how to find the domain of the inverse, therefore we don't know how to find the range. The only other way is you need to do the guessing and then find what number we need to avoid. But that's actually a very hard thing to do. Sometimes we can do it, sometimes we cannot do it. And of course, that is not an acceptable method to find because it's very not systematic. Too much guessing game there. Okay, so what we learned from this example is the one that's very, very important. What we learned from this example is this big note, the domain of inverse function is equal to the range of the function. So if you want to find the range of a function, one way to do it is to find the domain of the inverse function. Okay. I know this part is already on the precalculus side. Now let's do something even more. It's even harder. What if if the function is not one-to-one. Even if the function is not one-to-one, we can always find the inverse. The problem is that inverse is not a function. The inverse always exists. And I know a lot of instructors disagree with me here, but it's more about philosophy. Okay, when we think about the word inverse, does it have to be always be in terms of a function? You know, if when we say inverse has to be a function, then the answer is no. Okay, the inverse function of a function may not always exist. Okay, we only have the inverse of a function to be a function if the original function is one-to-one. If the function is one-to-one, then the inverse is also a function. And once the inverse is also a function, then it has the right. It has the right to use that inverse function notation. Now, otherwise, then it has the inverse, but it's not a function. Now, let's take a look. Let's take a look on a small example. Let's say, for example, the easiest one. I think we have that one earlier. Let's say fx equals to fx equals to x squared. Now, this is not a one-to-one function. This is not a one-to-one function. Can we find the inverse? Yes. Is the inverse a function? No. Okay, now, how do we find the inverse? We did the same way we did earlier, but we just cannot finish up to step number 4. We can only go up to step number 3. So step 1. Replace fx by y. Step 2, we swap x and y. Step 3, y equals to plus minus square root of x. Okay, so this is the inverse of fx. However, because the fx is not one-to-one, this is not one-to-one, then the inverse is not a function. Therefore, we have no right to write that as f inverse x plus minus square root of x. Now, we cannot do that. We have no such right because the other side here does not define a function. Everybody okay with this?
Yes.
Okay, so if the function is not one-to-one, we still can find the inverse, but we cannot write that as inverse function. Now, however, like what we said earlier, how do we find the range of a function? How do we find the range of a function? We actually look at the domain of the inverse. So it doesn't have to be inverse function. We just need to look at the domain of this inverse. You see what I mean? So you can start at step 3 and see what's the domain there. Now, let's see. If we look back, what is the domain? What is the range of this fx equals to x squared? the graph is that basic x squared parabola, right? Okay, so the range is from 0 to infinity, not the domain, the range. Do you notice that? Now, compare with the domain of the inverse. If you look at this, what is the domain? That's the set of all x where x has to be at least 0, right? How do I know? Because inside the radical, it has to be non-negative, right? Now, when I write that in interval notation, that's basically the range of the original function. That's the range of the original function. You see that? Okay, so one of the big purpose we learn inverse function, of course, is for 4.2 and 4.3, but the side kick that we get from here is then we find another method to find the range of a function. Now, of course, if we are lucky, if the function is one-to-one, then the range of that function is the domain of the inverse function. But even if the function is not one-to-one, the range of that function is still the domain of the inverse. Now, let's take a look on the next example here. This one is quite tough. In fact, this following function is a quite well-known function for higher analysis, higher math. X plus 1 over x. I do expect that you are able to graph this function. This is x squared plus 1 over x. Okay, so we know what's the domain, right? The domain is all real numbers except 0. Okay, there's no x-intercept, there's no y-intercept. We have vertical asymptote x equals to 0. And we should have a slant asymptote because the degree on the top is 1 more than the degree of the bottom. Let's just find it out. So if I divide, x squared plus 0x plus 1, and I divide by x, I actually have it here. What am I doing? When I divide it, then I will get this and as the quotient and this part here as the remainder, right? Therefore, the slant asymptote will be y equals to x. Okay, but the question that I could not ask you before, now I may be able to ask you already. How do we find the range? Okay, now let's work it out. To find the range, then let me find the inverse. I know this is not a one-to-one function. Okay, it's not a one-to-one function. In fact, if I try to sketch that, I think it looks like this. It looks like this. And this is the slant asymptote. Yeah. Well, I can graph that later on with the graphing software that I have. I can show you that later. Okay, but the thing is, how do we find the range? Now, the range should be from negative infinity up to certain y there, and from certain y here goes up to positive infinity, right? But I don't know what is this here. I need to find what are these two boundaries there. Okay. Now let's try to do that formally. what I will do is I will try to find the inverse of that function. I know this function is not one-to-one, so the inverse is not a function. So xy equals to y squared plus 1. How do I solve for y here? It's a quadratic. Right? So what I will do is I will use quadratic formula. I will use quadratic formula. Okay, where my a equals to 1, my b is negative x, my c equals to 1. Remember, I'm solving for y. I'm not solving for x. I'm solving for y. So y equals to negative b plus minus square root of b squared minus 4ac over 2a, which simplifies to be x plus minus square root of x squared minus 4 over 2. Now, that's the inverse. Remember, this is not inverse function. The inverse is not a function, especially because that we know it's a plus minus here. So we may have some x's that give us two different y's. Okay, so I cannot go to step 4. I cannot go to step 4. However, I don't need step 4. I don't need to write the inverse function. I just need the inverse. Now, you look at that inverse, and what's the domain of this inverse? Domain of this inverse is all x where x squared minus 4 has to be at least 0, right? The y will not be defined or not a real number if the radicand is negative. So this guy here has to be at least 0. Is it okay? Now, once we are able to find the domain of this inverse, then we will get the range of the original function. But then how do we solve this though? And we look back. That's something I did teach you in for your test 1, how to solve nonlinear inequality. So step 1, you remember that? Step 1, critical numbers, x squared minus 4, set it equals to 0. So x plus 2, x minus 2 equals to 0. So critical numbers are negative 2 and 2. Now step 2, the sign graph. Negative 2, positive 2. Both of them the zeros of the function, zeros of x squared minus 4. And then if we happen to know the graph of x squared minus 4, it's like this. So this is negative here. Well, you see that's the y-intercept, 0, negative 4. This is plus, this is minus, this is plus also. So the solution for that inequality is negative infinity up to negative 2 bracket union 2 to infinity. That's the solution of this inequality, which is the domain of the inverse. Which is the domain of the inverse. Okay, this is the inverse here. This is the inverse here. Now, even though the inverse is not a function, but we still can find the domain, right? Now, and then the domain of the inverse, therefore, give us the range of the function. Now, if you watch the lecture videos from YouTube, I don't think those lecture videos talk about this technique, you know. And to be honest with you, if you ask this question in the math lab, wherever math lab you can find, let's say they have an online math lab, and the tutor never see this technique, then the tutor will do it with calculus 1 method, in which they do something called derivative thingy. No, it's not doable that way. Okay, we cannot use. Yes, the video doesn't show this method at all, because this is a bit more advanced for intermediate algebra, and you can consider this as sidekick, the consequence of finding the range of the function using the technique that actually our textbook teach us, but because they don't break the finding the inverse function into 4 steps, then they never see that we can use this technique to find the range of a function, even if the function is not one-to-one. Why? Give me a second. I'm sorry. I wonder why my notes frozen. Okay, that's good. So now we get the range. Let's see even better view. Let's take a look on the graph. Share the graph. Let's go on the graph. Okay, that's the graph that we had before. Y equals to x plus 1 over x. Oops, no, not 1 over x. This is the function. This is the graph of the function. Can you see that, the graph? Can you see the graph? Am I on the same
Yes.
page?
We see the graph, yeah.
Yeah, okay. Now then, let me copy these to our notes. Too far here. Yeah. Now, the thing is then, how do we see the range here? We know that the range starts from here, right? Going up. And from here, going down. You see that? But you cannot judge a book from its cover. You cannot tell the range by just looking at the graph if you have such kind of graph. We need to super zoom this to make sure that it is true. And there's a big chance we still get it wrong, right? So the only way we can really get that, oh yeah, the range is from 2 to infinity, union negative infinity up to -2, is by using the technique that I taught you earlier. Okay, which is finding the inverse and find the domain of that inverse. That will be the range of the function. Okay. Now, I still have 10 minutes. Let me move this. I wonder if I can move this. Oh, I cannot. Let me ask you to do the following problem. Let's say, for example, find the range of fx equals to x squared plus 2 over x minus 1. X squared plus 2 over x minus 1. When you try that, give you the graph here. The graph says that it will be from some positive number up to infinity union negative infinity up to some negative number. But the thing is, we don't know precisely what is the y here. We don't know. We know it's more than 5 for that, and for this one is less than -1. Okay, let me start working on that. You do that, I do that too. So from here we see the a equals to 1, the b is -x, and the c is x plus 2. The coefficient of x squared is 1, the y squared is 1, coefficient of y is -x, and the constant part is x plus 2. Therefore, my y equals to -b plus minus square root of b squared minus 4ac over 2a. That simplifies to x plus minus square root of x squared minus 4x minus 8 over 2. So the domain of the inverse is equal to the range of the original function, which is what we're looking for, and that is all y where y squared minus 4y plus 8 greater equals to 0. And how to resolve that? Then step 1, critical numbers. Y squared minus 4y plus 8 equals 0. Oh, I'm sorry, not plus 8. It should be minus 8. Yeah, minus 8. My bad. I copied it wrong. Should be minus here. Erase this. It should be minus. Should be minus. I wrote it wrong earlier. Oh, it should be minus. So y squared minus 4y equals to 8. What number do I add to both sides?
4.
So I get y minus 2 squared equals to 12 the square root property. Fast forward, this is y equals to 2 plus minus square root of, square root of 12 is what? 2 square root of 3. Then when we do the sine graph, 2 minus 2 radical 3, 2 plus radical 3, 0, 0, negative y-intercept, positive 2, positive 2. I need the negative branch. So I will get negative infinity up to 2 minus 2 radical 3 union 2 plus 2 radical 3 comma. Now, if you use your calculator, then I believe what you get here will be approximately negative 1 point something. And what we get here will be 5 point something. Now, how do I know? From the graph. I happen to have the graph, right? Okay. Now the thing is, when you take your test, the assumption is you don't use graphing calculator. Even if you use graphing calculator, even if you get graphing calculator and you do the tracing, you will get decimal, right? You will not get a precise answer like what I get here. In fact, that's actually how I know that if you don't show work and suddenly you come up with the right answer but good approximation, like negative 1 point something, 5 point something, nah, you didn't do it right. Okay, you didn't do it right. You must be either guessing, cheating, graphing, but not accurate. Okay, now this is the correct way to do this. Now to summarize, this is 11:55 already. I'm about to stop. Here's the thing though. The range of a function is actually one of the big topics that we try to cover in Precalculus. But even with this method that I show you here, there are still a lot more functions that we cannot find the range. Okay, so there are plenty of functions that we dealt with. We can find the range already, like linear function, for example, or any polynomial with odd degrees. Any polynomials with odd degrees, then we know that the range must be all real numbers, right? Okay. If we have a one-to-one rational functions, we may be able to find the range also, but there are a lot more other group of functions we cannot find the range at all with whatever technique we learned so far. But with this technique that we have here, it opens one big door for us to find a range of some strange function that we didn't expect before. Okay, I will end the lesson today. I actually finished it very well here. So let me give you the suggested homework. Suggested homework for this 4.1. Hold on, I have a question. Okay. Suggested homework for 4.1 will be from number 1 to number 47. Number 1 to number 47. I think you can just do every other odd. Just do the odd ones then. Okay, and then from 3.6, number 1 to number 19 is good enough. So 3.6, number 1 to number 19. Just do the odd ones. Okay, that's for today. See you then on Monday.
Goodbye. Thank you.
Goodbye. See you.